Hello everyone, I'm Byun, and I'm a graduate student in Seoul National University. In this video, I'll explain the stability and robustness analysis of plug-pulling tasks using an aerial manipulator. Generally, the aerial vehicles are usually utilized for passive tasks such as surveillance, remote sensing, and active perception. However, recently, the new aerial platform which combines the maneuverability of the aerial vehicle and the versatility of the robotic manipulator is gaining interest from aerial robotics research community. This new aerial platform is called Aerial Manipulator, and it conducts the active tasks such as grasping, valve turning, door opening, plug pulling, and etc. Among those active tasks, I focused on the plug pulling using the aerial manipulator because the large force exerted on the individual disappears and it necessarily induces the abrupt change in dynamic model. In this perspective, I thought that there needs an elaborate analysis on the stability and robustness of the aerial manipulator conducting plug-pulling tasks using the concept of hybrid automata. So, the purpose of our research analysis follows. At first, we aim to formulate hybrid automata including three flight modes which consist of wire pulling, stabilizing, and free flight modes. Also, we plan to design trajectory generation strategies and corresponding disturbance observer-based controllers for the respective flight modes, and prove the stability and robustness of the aerial manipulator with the proposed controller. In addition to this, we arranged the related work to highlight the necessity of our research. For the aerial vehicle involved in the physical interaction, these three works arranged the dynamics using the concept of hybrid automata. However, they didn't prove the stability and robustness during the flight mode transition, and the change of the flight mode do not induce the abrupt change of dynamics like the plug-pulling operation. On the other hand, those two works here also arranged the dynamics using the concept of hybrid automata and also conducted the stability and robustness analysis. However, the change of the flight mode does not still induce the abrupt change of dynamics because they only dealt with the task which only entails small amount of dynamics change such as wall contact or landing on the inclined surface. Those tasks can reduce the degree of dynamics transition by approaching with small velocities. Compared to the related works, there are some contributions of our work. First, to the best of author's knowledge, it is the first time to conduct a plug-pulling task which necessarily induces an abrupt change in dynamics after the plug separation. Also, we present a thorough analysis on the stability and robustness and design a disturbance observer-based controller for the wire pulling mode based on the dynamic model of the aerial manipulator, which is constrained to the wire and the socket. From now on, let's take a look at the method part. First, I'm going to talk about the hybrid automata of the aerial plug-pulling vehicle. The plug-pulling aerial manipulator consists of three operative modes. The first one is the wire pulling mode, which tilts its body to pull the plug out of the socket. And the second one is the stabilizing mode, which rapidly makes the altitude of the multirotor to the hovering state. And the final one is free flight mode, which demonstrates the freely flying aerial manipulator. And the domains for each operative mode is arranged as follows. Intuitively, you can realize that the plug is combined to the socket until the interaction force in pulling direction exceeds its threshold value. Therefore, the domain for wire pulling mode is defined as follows. However, for the stabilizing and free flight mode, the domain is the same because there is no dynamics difference. So whole space in the experiment except for wire pulling domain becomes the domain mappings for stabilizing and free flight modes. And the flow maps, which describe the dynamics for each operative mode, are analyzed as follows. For the wire pulling mode, we derive the dynamics using the fact that the end effector is constrained to the fixed point while it can freely rotate with respect to the point. So the generalized coordinate for this mode, R, can be expressed as the collection of Euler and servo angles. Also, if we set the control input UF as the combination of total thrust and body torque, it can be used as a general expression of the control input later on. For the stabilizing and free flight mode, we can easily derive the dynamics of the aerial manipulator using Euler-Lagrange equation. For these two modes, the generalized coordinate consists of the position, all angles, and servo angles. And the Gauss mappings, which mean the condition for the mode transition, are also arranged as follows. As you can see in the previous slides, the mode change to stabilizing from wire pulling occurs when the interaction force on the end effector exceeds its threshold value. So technically, the Gauss mapping from wire pulling to stabilizing mode is formulated as in the box. Also, since the difference between stabilizing and FF mode is the way of controlling the vehicle, there is some conditions that the operative mode change occurs. As the name of stabilizing, mode change to free flight occurs when the altitude values become close to zero and after the certain time period. And to avoid the undesirable mode change, such as direct transition from wirepulling to free flight mode, can be prevented. And for the last part of the hybrid automata, the recent maps, which mean the change of state values before and after the mode transition, are arranged as follows. When the operative mode is changed to the stabilizing mode from wirepulling mode, the speed of the end effector becomes non-zero when the plug is separated from the socket. Thus, the formal set expression of this mode transition is formulated as shown in the box. However, for the transition from stabilizing to free flight mode, since there is no discrete state jump in stage Q and Q dots, the recent map is derived as follows. Next, I will talk about our trajectory generation strategy. The main point of our trajectory is continuity. To fulfill the criteria of the given controller, we try to maintain the continuity of the reference trajectory. For wirepulling mode, it makes the reference to make the multirotor stall slightly tilt its body to the pulling direction. The reference point becomes constant when the multirotor reaches its maximum pitch angle theta m. And after the plug separation, a rapid trajectory for altitude stabilization is generated as shown in those figures. In a short period between T0st and TDst, the desired pitch angle rapidly goes up to zero, while the reference point of the altitude remains the same as its value in initial time of stabilizing mode. And when the free flight mode is reached, it simply holds its position and maintains its hovering state. Also, the controller is derived according to its operative mode. For the wirepulling mode, to get the body torque input, we first formulate the nominal model of the wirepulling dynamics as follows. In these equations, M eta, C eta, K eta, and J eta are block matrices from MR, CR, KR, and JUR, while the bar sign means the nominal values, which consist of the measured mass, measured length, and measured moment of inertia. Also, the hash sign means the estimated value from Kalman filter. And from the nominal control input tau be 0, which makes the nominal model asymptotically stable, we can get the body torque tau b by the proposed disturbance observed structure shown below. For the stabilizing and free flight mode, we use controllers from reference papers 6 and 7. For the stabilizing mode, we turn off the controller for the under-actuated part and generates the reference trajectory of altitude and all angles following the trajectory generation strategies mentioned before. However, for the free flight mode, we turn on the whole controllers and try to maintain the multirotor's hovering state. And for the last part of our research's method part, I will briefly introduce the procedure of stability and robustness analysis. At first, we proved the robustness of the nominal maneuver, including flight mode transitions. To show the robustness of the nominal maneuver, there is two conditions. First, the desired mode transition from wirepulling to stabilizing mode should be accomplished while the undesired mode transition from wirepulling to free flight mode doesn't occur. From the detailed analysis on our scenario, we found out that the trajectory with our proposed trajectory generation strategies guarantees the mode transition from wirepulling to stabilizing mode while the transition to free flight mode never occurs. And the second condition is that the undesired mode transition must not occur after the mode transition and state jump. And from the Gauss mapping definition from stabilizing to free flight mode, there exists a temporal limit so that the direct mode change from stabilizing to free flight mode can be prevented. Also, while the stability proof for stabilizing and free flight mode are done in reference 6 and 7, we newly proved the stability and robustness of wirepulling mode by using the theory of singular perturbation and following the procedures of 6 and 7. As you can see in this similar theorem says that there exists epsilon star eta such that for each epsilon eta which is larger than 0 and smaller than epsilon star eta, the following inequality holds. Also, while the stability proof of stabilizing and free flight mode are done in reference 6 and 7, we proved the theorem 1 shown in the previous slide. First, we formulate the standard single perturbation form with respect to psi and zeta, which is the functions of p and q values, and we prove that the boundary layer system of psi and zeta is exponentially stable. And finally, we use Tikhonov's theorem to prove that the closed-loop system of wirepulling mode is ultimately bounded. And as I mentioned before, the stability and robustness of the stabilizing and free flight mode are proved in 6 and 7. Lastly, I will show you the experimental results. With our aerial manipulator and robotic manipulator, the plug plugged in this socket was pulled out. Also, I conducted the experiment with a long wire because the focus of our paper is to show the process of plug-pulling and stability recovery after the operative mode transition, rather than approaching the socket. If I use the PD controller based on the nominal model of wirepulling mode, as you can see in this video, the stability of the aerial manipulator cannot be maintained. However, if we use the proposed controller and trajectory generation strategies, if you closely look at the plot of pitch angle, it is shown that the controller was well working. So, to summarize, the concept of hybrid automata is used to demonstrate the aerial plug-pulling with 3 operative modes, and the trajectory generation strategies and disturbance observer-based controllers for each operative mode are also formulated. In addition to this, we proved the overall stability and robustness, and we conducted an actual experiment and showed that the pitch angle well follows its reference and the stability is maintained after the plug is separated. And for the future works, an autonomous grasping of a plug with an aerial manipulator can be included in the experiment in the future. These are the reference papers that I used in this video, and this is my end of presentation. Thank you for listening, and if you have any questions, please contact me via the information shown here or attend to my spotlight presentation.